Hello everyone, I'm Sergio and I'm going to expose this work. This work is named as Mapping Optimization for MPI Collective Operation based on reinforcement learning. Here we have the index, which basically defines the points which we are going to see in this presentation. We have the introduction, the problem definition, the implementation of the reinforcement learning algorithm, how we have implemented the reward function, the results, and the future work and conclusions. I want to start talking about this quote, which has been made by Nika Simagilova in 2018. It basically, what it says that the convergence between machine learning and future exascale environment is very important, and this can be a key point to develop a powerful supercomputer and productive distributed system in the world. So first we have the introduction. In the introduction, what we have say is that we have main points. The first one is the data incrementation during the past years. This was pointed in the previous quote, and it is a main factor to have into account when talking about HPC and its application. The second point is that HPC obviously is a need to process the amount of data and actual complex application. This is because we need a platform which is able to speed up the computation and the communication. As we can see in the figure in this slide, we have HPC platform composed of different devices and composed of different number of GPUs or CPUs. This produces that actual HPC platforms are very heterogeneous. The next point is directly connected to the previous point. We want to optimize the performance of application, and the goal is to obtain the high possible performance in this application by balanced technique of computation and communication. The next point is basically what we want to focus in this work, and it is reinforcement learning as optimization. I want to explain here a little bit of how this works. Basically, we have some components. The agent is an object which interacts with the environment, doing some actions. The environment is a description of the world where the agent acts. In every tiny step, the agent selects an action, and this type of moves have consequence, is what we call rewards. Rewards are assigned to the transition of between states, and it can be positive or negative values. The actions are done following a probability distribution, and finally the policy defines the way of how the agent behaves in a specific time step. So basically the policy is what the agent learns, and the final goal is to maximize the rewards through this number of time steps, which it's called as trajectory. So now we have the problem definition. As we know, in typical HPC application, we have MPI collective, which are usually implemented as sequence of point-to-point transmissions, building a graph of communication. In this slide, we have a figure where we can see this behavior. We have different rounds of communication, and process sends different messages between rounds. The optimization objective of this type of collective is to match the implemented virtual topology to physical process. Is what we know as mapping. Basically, there are two techniques in the literature with optimal, define, and mapping. These techniques are analytical communication models, which basically defines a number of parameters as the number of processes, the size of the messages, and the network topology. Secondly, we have the methods that search for an optimal mapping given a description of the communication performed by an application and its collective algorithms. So this type of techniques have different problems. It works very well with homogeneous system where the devices are the same, but with heterogeneous system it introduces an additional complexity that leads to suboptimal decision. This is a work which uses analytical performance model to model the communications. We have multiple parameters to model in this work. As we can see in the equation, we have a transmission through a communication channel. The transmission is point-to-point of a message size. It has different parameters as the overhead and the number of transmission through a communication channels, and tau, this parameter which defines the concurrent transmission. What we propose is a mapping optimization based on reinforcement learning to achieve the following goals. We want an offline policy-based method to build optimal graph for MPI collective. We want to avoid the profile of the different parameters involved in the communication and the computation. We want it to be optimal for heterogeneous environments. We have done this using a reinforcement learning algorithm, and our work is inspired by Moreno, who distributed the workload for efficient execution time of the placement of operation from an execution graph of a neural network. Moreno wants to minimize the time of the computation of the neural network graph. So it defined an objective function which is the expectation of the rewards following a policy of a neural network graph. We want to do something similar, but we want to use the policy gradient reinforced algorithm. This algorithm basically acts as shown in these points. We have an agent that learns a parameter policy. We want to approximate the policy using a neural network, and at each time step t, the action probabilities that maximize a defined objective in a state are reinforced positively by using the gradient of such objective action. So we have the actions that compose a trajectory, which are sampled using the parameter policy. We have here the equation, which basically is the reward of a policy obtained using that policy is the summatory of the rewards of all time steps using multiplied by a discount factor. This factor is used to avoid the reward grown to the infinity. So we have an optimization problem, and we want to solve this as the maximization of the objective function, which basically is maximizing the reward. The final step is the gradient calculation, which is the equation are shown in the slide, and we have also the policy parameter update, which basically works as an usually neural network backward pass. Here in the slide we have an example of how this mapping works. We have the time step 0, where we have the action 0, which maps the process 0 to the node 0. We have in blue, in dark blue, the action which is taken in this time step, and in the light blue color we have the action we haven't been done in this time step. We are going to build this graph during the following time steps. In the time step 1 we have how the action 1 maps the process 1 to the node 1, and we are going to follow all this time step until we have the MPI collective mapped to the process of some nodes. We are going to see this later on the results part. We have also developed a reward function. And this step is very important because it has different problems which basically cause high variance in the estimation of the objective function, and this problem are caused by because the trajectory is always the same. It is improved using a reward to go better than space rewards, which we will see later also. And we want to generalize scenarios to avoid high training times. So we have made a reward to go function which basically work as shown in the slides. We have the summatory of the time step, and we divide the reward of that time step between the maximum of the obtain the maximum possibility of the reward of that time step. This way, what we do is avoid sparse reward, and we have reward to go function which works very well in this scenario. This is an example of how this works. We have a simple MPI collective, and in the first step we map the node 0 to the process 0. In the following step we continue until we have all the collective modeled. So now we have to evaluate the rewards, and this is so as in the first step we have that the process 0 sent to process 1, and we assign a reward of 2 because the process are in the same node. In the following step we have that the process C1 sent to the process 3, so we have a reward 0 because the communication is not done in the same node. The same happens in the communication of 0 between to 2. So to end with this, we have the results. We have done these proofs into different MPI mappings. So we have, in this slide, we have 8 processes and 4 nodes for a collective, which is a binomial broadcast. We have shown that the rewards grown very well until the maximum is reached, and we have seen that the loss function works really well until it fits to the minimum. This is an example of how the collective is done. As we can see, the communication between the process in the same node are favored. So we have that always the leaf nodes are in the same node as its parents. As we can see, 7 is in the same node as 3, 5 is in the same node as 1, 4 is in the same node in the same node as 0, 0, and 6 is in the same node as 2. The next result is 16 profs with 8 nodes, and the collective is binomial broadcast. It works similarly as the previous result, and we have here the mapping, and we can see that the behavior is really similar to the previous one. So we have the conclusion, and we can conclude that reinforcement learning algorithms are a research of line of interest to optimize HPC typical application as mapping or scheduling. One of the main reasons is that they are able to optimize application without knowing all the parameters that have impact in the computation and communication. The future work is to study this proposal in environment with more process and nodes, and hence we want to increment the scalability of these results. Also, what we want to do is implement more MPI collective to have a generalized method. This is all, and if you have any question, I am going to be here in the room, so I am able to answer everyone who wants to ask something. Thank you so much, and this is all.